So hi everyone, thanks for coming for the second talk of the String Field Theory Journal Club for this 2023-24 session. So we are very happy to have Minjae. So please, Minjae, you can start. So you have 1 hour and a half, and you can arrange as you want. Thanks again for agreeing to
Thank,
speak.
thank you, Harold. I wish to first start by thanking the organizers for giving me the opportunity to speak here, in particular towards this community of string field theories. So today I'm going to tell you about the symplectic form of the open string field theory. And this is based on my recent work with excellent graduate student at Harvard, Ben Mazel, and also Sheehan. And you can find the complete detail in our preprint on the archive. And let me first start by listing out several motivations to talk about, this object called symplectic form in the open string field theory. So the first motivation really comes from the fact that, thanks to many people in this community, there exists many interesting classical solutions to open string field theory. Like, for example, we know, thanks to, for example, like Carlo and Coliberi's work, we know that all the d-branes can be represented as a solution to open string field equations of motions, at least in the Bosnian open string field theory case. So it is natural to ask about the space of solutions. Okay? And one can ask, what is its structure? Is it just some manifold? Is it equipped with some form? And so on. Okay? And let's bring the comparison against the cases where we understand this notion of space of solutions really well. And that is the case of the usual phase space in the context of classical Hamiltonian dynamics. Okay, so what do we mean by phase space? It's literally the space of solutions to some given Hamiltonian system. And that's not the end of the story. It has some structure. In particular, we all know that it is equipped with something called symplectic form. In the simplistic example, this is what we write down. It's dq/dp, where q is the position and p is the momenta. And we can also talk about things like Hamiltonian vector fields. We can also talk about what are the charges which generate such flows, and so on. Okay, so this is a very familiar notion in the classical mechanics. And the question is the space of solutions of the open string field theory, at least the classical one, something like this? And we are actually going to see that it's exactly like this. And surprisingly, so I gave you the motivation, which is that, okay, we found many interesting solutions. But it turns out that even before we found all these solutions, this notion of space of solutions was discussed. Already by Witten, back in '86. Okay. By the way, this is not the first paper, where he introduced the cubic open string field theory. This is actually the one on, super cubic open string field theory. I mean, of course, by now we know that this itself is not quite complete because of the singularities. But what's interesting is that this paper actually, even in recent years, keeps getting cited by people outside string field theory community. And it's because it talks about the notion of phase space. And in particular, he doesn't just like limit his discussion to the open string field theory. He actually introduces something called covariant phase space formalism. And because this is one of the first papers to do so in our field, this paper keeps getting cited by people studying, say, higher derivative theory and gravity theory and so on. Okay. So, well, for us, the upshot is that he already formulated the idea of open string field theory phase space. It's the space of solutions. He defined the symplectic form and so on. As I will describe later, it turns out that his description is not quite complete. There are some subtleties, and our contribution is to basically clarify the subtleties and actually make use of this type of symplectic form to compute something physical. Okay. Any question about this first motivation before I go to the next one? Okay. So now let's come to a more physical motivation. Okay. Before it was more like, okay, there is this mathematical structure in the classical dynamics, and can we define such a thing on open string field theory? Now let's come to the somewhat more physical motivation. The motivation actually comes from a very famous solution of open string field theory, which is called open string rolling tachyon. Okay, and it is a beautiful example of possibly many time-dependent solutions of open string field theory. And Ashok's seminal paper in 2002 started all this discussion in our field. And you can, for example, look at this big review for a comprehensive introduction and review. So let me give you the physical picture. So say there exists some unstable d-brane due to open string tachyon. Okay, and pictorially we draw this type of picture. So we have a tachyon potential, which looks like this. And then this origin is basically the productive vacuum. Which represents the unstable d-brane itself. It's a static solution, but it's unstable. So now, if you look at this just like the usual ordinary classical mechanical system, a natural question is, okay, what happens if you just, slightly hit it or like place it a bit towards this side? Then we expect that it's going to roll down. And this is called rolling tachyon. And it can be also thought of as a d-brane decay. And this is a time-dependent procedure. So if such a solution indeed exists, it's going to represent time-dependent solution of open string field theory. And turns out that one can actually construct such solutions. And what Ashok noticed in his seminal paper was that there are two pictures. You can construct a solution productively in terms of the deformation. Well, you can also construct the exact boundary state corresponding to this time-dependent solution. So what is the question that one can ask about such solutions? And those are the natural ones, like what is the charge of such a solution? And in particular, the one which was addressed originally in Ashok's paper was the energy of the rolling tachyon solution. Yeah. So originally, this energy of the rolling tachyon solution was conjectured by Ashok, but later it was actually justified from the perspective of open-closed string field theory. So the story here is like the following. So why all of a sudden we are talking about closed strings? It happens that, as explained nicely in Barton's work in 97, if you have open-closed string field theory, and if you consider rigid gauge transformation of the closed string sector, that actually realizes the global symmetry acting on the open string sector. So for example, this is how the Poincare transformation, which is realized as a gauge transformation of the closed string sector, can also act on the open string degrees of freedom. And by working this out systematically, Ashok actually showed how to obtain the energy of the open string solution. But at the same time, this raises a question, okay? And the question is the following. This rolling tachyon solution is a solution to purely open string field theory, right? So is there a way to understand this quantity purely in terms of open string field theory language? Okay. As I'll demonstrate throughout this talk, that is the case. That is actually the purpose of symplectic form. Okay. So roughly speaking, when we write symplectic form as dE dt, for example, we know that E, energy, is what is generating the time translation. So as soon as you write down symplectic form, you already have idea about what is the charge which is generating specific Hamiltonian flow. And finally, the very original motivation for me, Ben, and Shi to visit the notion of phase space was the following. So if you look at Ashok's paper, say the O4 review, he makes very outstanding conjecture, which is something called quantum open string field theory, sometimes called open string completeness conjecture. So what he was suggesting is the following. So de Bruijn decay, you can imagine that as de Bruijn decays, there are closed strings radiated and so on. But he said that actually to describe the complete physics of this rolling tachyon, one might not need to talk about the closed string degrees of freedom. Actually, open string field degrees of freedom already contains all the necessary degrees of freedom to describe the physics, including such decay of the de Bruijn and radiating closed strings. So that is known as quantum open string field theory. And our naive attempt or idea was, okay, what if we quantize the classical phase space and obtain such a quantum open string field theory? Okay. I mean, we are not there yet, but our original motivation really was this one. And for that purpose, we thought that we better understand what we really mean by classical phase space. Okay. And yeah, we somehow found that Witten's paper already discussed this, and that's how this project started. Any questions before I move on? Everything good? Good. So now let me come to something called covariant phase space formalism. Okay. I guess many people in this audience already know what this is, but let me introduce it anyway. If you want to read a good review paper on this, you can read this beautiful paper by Harlow and Wu. I mean, this is both a paper including new results, but it's also a very nice introductory material, especially for people like me who had no previous experience with the subject. For today's purpose, we are not going to need the most general discussion of covariant phase space formalism. Rather, we are going to focus on a very specific toy example. And it turns out that that serves the purpose, at least for today. And let's consider the simplest classical mechanical system, free particle. This is the action. Where Q stands for the position of the particle, which depends on the time. And now, once we are given the action, the very first thing that all of us are tempted to do is to vary the action. That's what we have been doing all along. So let's do that. We vary the action. And this is what we get. Okay. And we do not declare a victory yet. We declare a victory only when we actually succeed in moving this one derivative in the variation to the other side. And what do we do in order to achieve that? We do integration by parts. Good? Okay. And typically we say, okay, we are going to consider solutions which do not have boundary conditions and blah, blah, blah. And what do? We just ignore this part. Okay, that's what happens most of the time. And of course, this second part is very familiar. This is what gives rise to the equations of motions. Okay. It turns out that the key player in the story of symplectic form in the context of covariant phase space formalism is actually this first guy, the total derivative term. And in particular, this one, the one inside the total derivative, is something called symplectic potential. Okay. And we are going to see what role it plays very soon. But okay, let's continue our classical mechanics exercise. We have equations of motions. It is a very complicated one. But fortunately, we know how to solve it. All it's saying is that, okay, our solution can be at most linear in time. So this is one way to write down the solution, where we have two parameters, P and Q naught. And P basically stands for the velocity of the particle, or momenta, and Q naught stands for the initial position. And we can parameterize it in other way. For example, we can write it like this. And what is manifest here is the notion of U, which is saying that solutions related by different values of U are related to each other by time translation. Okay. So what have we achieved by solving this equation? We notice that this P, Q naught, and U are the parameters which parameterizes the phase space. Okay. So again, phase space is solution, space of the solution. And here, what we are seeing is that, okay, we can explicitly parameterize such a space using two real parameters. Either you use P and Q naught, or P and U, or you can use any other parameterization you want. So we now have this very simple, simple notion of phase space. And what do we do with it? Okay, that's the question we are asking. And this is where we introduce symplectic form. By the way, any questions so far? Is everything clear? Good. So symplectic form is the place where a conceptual leap happens, okay? So originally, when we were varying the action, this delta was really thought of as a variation, okay? But now, when we consider this symplectic potential, we are going to consider this delta as an exterior derivative acting on the phase space. And that kind of makes sense. Like if we are talking about delta acting on Q, like here, and if we confine to Q's which are given by the solutions, then it's actually natural to consider this delta as acting on the parameters like P, Q naught, and U, which parameterizes the phase space. So with that perspective, the symplectic form omega is actually written like this. So this is a symplectic potential. We bring it to here, and then we are going to take one more exterior derivative. Okay, that's the prescription. I didn't explain the reason for doing this yet. That's the prescription, and let's see what we get. And, you know, because now we consider it as an exterior derivative, it squares to 0. So this delta can act only on the second one. So what we get is dq dot. And again, let me emphasize that this variation is now viewed as an exterior derivative on the phase space.
Hi, Minjae. Can I ask a question?
Oh, sure.
Yeah, hi, how are you?
Good, how are you?
So this depends on, this depends on the boundary condition that you impose, right? Like if you impose a different boundary condition for your action.
That is absolutely true.
It's going to change, right?
Yeah. So actually, if you look into this beautiful paper by Harlow and Wu, actually the purpose of the paper was to demonstrate all the subtleties that you may run into as you describe the presence of boundaries and what type of boundary condition you impose and so on. But yeah, for this simple system, I'm just going to be ignorant about the boundary conditions because for this simple system, we don't need to talk about that. And fortunately, for the application that I'm going to describe later, which is the rolling tachyon, I also don't need to talk about it. Yeah, so
okay.
But you are absolutely right in that one has to discuss the boundary conditions, and there are subtleties which arise in such cases. And this paper nicely describes several of such examples. Yeah. Thank you for the question. Good. So what have we achieved? What we have achieved is to come up with a two form. So see, this has two exterior derivatives, so it's a two form. We obtained a two form on the phase space, and because we obtained it by taking exterior derivative, it is closed, and one can actually also show that it is covariant. Non-degenerate. So it's a non-degenerate two form on the phase space, and that's the definition of symplectic form. So let's be explicit. Why not? Because we have explicit expression for the solution. So consider this solution parameterized by P and Q naught. Delta is going to act on P and Q naught because those are the parameters parameterizing the phase space. Okay. So we just use chain rule. It's a very simple one in this case. Okay. And the second ingredient for the symplectic form was delta of Q dot, and we obtained this one. Okay. So, okay, let me also write down how this looks like if we use P and U variable. It is straightforward to write it down. And this is what we get. Okay, it's very easy to just plug these expressions in and see how you get these things. Okay. Well, at this stage, you might actually worry about something, which is that we have explicit appearances of T. And typically, when we say that okay, we want the Cauchy initial value problem to be well defined and so on, we actually want symplectic form to be independent of how we choose the initial time and so on. Well, turns out that that is indeed what we have once we write out the full expression for the symplectic form. So, from this one, dq dot is just given by dq naught dp, because dp and dp contrast, once we multiply them each other, they become 0. In terms of u variable, what we obtain is the following. Okay. And recall, what was u? U was basically the parameter for the time translation. And in the symplectic form, what this is saying is that, okay, the charge which is generating the translation in u is actually given by p squared over 2. And we know what the meaning of p squared over 2 is. It is the energy. It's the energy of the solution. Okay. Another way to say this is like the following. Okay, if we define the differential of the energy as symplectic form contracted against the time translation, this is a vector, tangent vector which is generating the time translation, then yeah, this is the notion of energy that we are after. Okay. All I'm saying here is very simple. What I'm saying is that, okay, once you write down the symplectic form, you actually know which charge generates which Hamiltonian flow. And this is how symplectic form encodes the information about physical quantities, basically the charges of the solution. And the question for, say, open string field theory will be if you have, say, rolling tachyon solution, and if you can write down this type of symplectic form, and if you evaluate the symplectic form on such rolling tachyon solution, then you can actually write down this type of expression, and you can identify this guy as the energy of the solution. Is everything clear? Okay, this is the simplest example of free particle, but it is non-trivial enough to serve as a good introduction to symplectic form and covariant phase space. One thing I forgot to say is that, okay, once you write out this symplectic form, now you see that it's no longer dependent on the variable t. I mean, it's not a variable, it's time t. And also, for that reason, it is also independent of how you choose the initial time. Okay. So let me briefly mention what happens in more general Lagrangian theory. So consider more general Lagrangian theory. It's a Lagrangian together with set of fields and their derivatives. And typically we have action written as a Lagrangian integrated over some space-time manifold n. Okay. And we repeat the exercise that we've already done for the free particle. As we vary the Lagrangian, we are going to obtain this variation of the field part, which is multiplied by equations of motions. But then in order to organize terms into this manner, we actually have to perform integration by parts. So we pick up this total derivative term. So this d, unlike the delta before, this d stands for the space-time exterior derivative. Okay. And this u is the symplectic potential. Okay. In particular, it is proportional to variation of the field itself. So we can solve the equations of motions. What this is doing for us is that it gives us the notion of phase space. But we can go further. So from the symplectic potential, now interpreting this delta as an exterior derivative on the phase space, we can get the symplectic form. And it's typically written in this form. So we have symplectic potential. We take exterior derivative, and we integrate this expression over the Cauchy slice. This sigma is a Cauchy slice. So one may ask, it seems like this definition depends on the choice of Cauchy slice. Equivalent question that you could have asked in the case of free particle is like, does the symplectic form depend on the choice of the initial time? And we saw that it doesn't. And that's actually one of the key points about this construction. So if you follow this construction of deriving the symplectic form from the variation of the Lagrangian, it is actually guaranteed that this symplectic form is going to be independent of the choice of the Cauchy slice, as we hope. And in case of the gauge theories, it turns out that you can further prove that it is also gauge invariant. And so that's actually the reason for this tilde. If you consider phase space, which is not voted out by the gauge transformation, it's actually something called pre-phase space. And this symplectic form is actually something called pre-symplectic form. And that's actually going to be relevant for us because we know that string field theory is also gauge theory. Any questions so far? Okay. Now let's finally come to the notion of this symplectic form in the case of open string field theory. And for this one, I'm going to follow what was introduced in Witten's 86 paper. This is our beloved Witten's cubic open string field theory action. And we vary the action. We obtain this part, equations of motions. Okay, I think many people in this audience have expertise in dealing with this one. Of course, in order to obtain this form of equations of motions, we should have done integration by parts. And in our case, it is actually given by this QB term, which is a total derivative. Okay. So far so good. We have equations of motions. We can solve it, and that gives the notion of the phase space, which is the space of solutions to this equation. And now we can try to write down, repeat the exercise that we've done for the free particle case. For our case. So, okay, let's revisit what we did in the free particle case. Basically, we had total derivative term written in terms of, d acting on some u, and this u was the pre-symplectic potential. By the way, note that this d is one derivative. It's first order derivative, I should have said. In comparison, what we have in open string field theory is somewhat different. I mean, even though we know that it's a total derivative, we have to massage the expression because this QB we know is a second order derivative because BRST charge includes this matter stress tensor part, which in particular gives us second order derivative term due to these two terms. Okay, so basically what we have to do if we want to write down the open string field symplectic form, we need to effectively strip off one derivative from QB. Okay, so that the leftover, so say we stripped off one derivative and the rest is basically going to be this u. So how do you get first order derivative from second order derivative? It took me a while to understand how Witten came up with the final prescription. Actually, he doesn't explain in full detail how he arrives at his symplectic form. It's more based on, how should I say, following the notes. But somehow I couldn't follow his notes. But for me, at least, this simple exercise worked. So now let's consider the ordinary derivative. Okay, we have derivative in this t squared. And if you consider its commutator against the step function, you can actually show that it gives rise to a first order derivative. And not only that, it actually gives you something that localizes to t equals 0. Okay, so here we already see that if you introduce commutator against step function, then you also have notion of Cauchy slice. And you also succeeded in getting the first order derivative. Okay, so to me, this was the reason why Witten's prescription made sense. And his prescription was, okay, just replace this QB by its commutator with a theta function, which depends on the choice of the Cauchy slice. And let me explain what this is. Okay. I mean, in this case, it's very simple. It's a function. If we have t, this is 0. It's a function which is 0 all the way here, but then all of a sudden it becomes 1 here. Right. In the case of open string field theory, this Heaviside step function is something that we define with respect to the open string midpoint. It is kind of expected because we all know that if we have to choose one specific point in written string field theory, it better be the open string midpoint. We know that it's the special point. So the definition of this Heaviside step function is that it is 1 if the midpoint is in the future of this slice sigma. It is 0 otherwise. Okay. Any question about this definition? I'm soon going to write down the explicit form of the correlator, which is going to compute objects like this one.
So I have a small question. So you say that the midpoint is the most natural, but why not the center of mass, for example?
Good.
I remember like Ted had a paper on causality, and I think if I remember, he was arguing that one of the two was more natural, but I forgot which one now.
Yeah, so in this case, one can show that if you write down the symplectic form in this way, you actually have the independence of the Cauchy slides, and it is gauge invariant and all of those things. Actually, it's kind of straightforward to see that if you chose any other point, then at least one of these properties will not hold for the symplectic form that one writes down. Yeah, I mean, yeah, it may be true that, like, you know, you can choose alternative point, but then I guess your definition of the symplectic form itself will be a bit different. Yeah.
Okay, thanks.
Yeah, thanks for the question.
Hi, Minjae. So
Yeah.
this, yeah, if I remember this Witten's paper correctly, this prescription is essentially coming from the demand that the symplectic form that you will define is independent of sigma at the end, right?
Yeah.
So is this like a unique way to do this, like this QB replacing by commutator of QB theta?
I mean, so if you want to write down the symplectic form that Witten wrote down, then this is the unique way, in the sense that, you know, if you choose any other point, then the symplectic form that he defined is not going to be independent of sigma or gauge invariant and so on. I don't know, like, it may be possible that you choose alternative point and then you define the symplectic form in an alternative way, and then those are related into each other by, you know, reparameterization of the phase space variables and so on. That may be possible,
Yeah,
but yeah, all I'm saying here
because yeah, go ahead.
Yeah, all I'm saying here is that
Yeah, so,
this is a way to write down a consistent definition of the symplectic form.
I see. So like my concern is that like somehow like you replace the second derivative with like a first order derivative, and like okay, this like it doesn't happen in the case that you show in the scalar field, right? But is it like say that is it?
Sorry. So you say the second
is that,
derivative does not appear in the case of, say, free particle.
Yeah. So what I was saying is that is there a way to like put the scalar particle so that the second derivative acting like this way and repeat the same this del t squared theta t, the toy example that you gave, and does it give the same expression?
I think it's essentially this argument.
Yeah, I see. So in the scalar case, there is also like a way to write so that the second order derivative is acting on it, so that you can do, you know, basically motivate this prescription.
Yeah,
okay, fair enough.
Yeah, it's literally this one.
Okay.
Yeah.
All right. Thank you.
Yeah, thank you. Any other questions?
Maybe another way to read it is that maybe like going from like not from left to right, but right to left instead.
Indeed.
I don't know. Yeah. Okay. Okay. All right. Thank you so much.
Yeah. Thank you. Good. So let me finally write down the symplectic form. So this is what Witten wrote down. So for the total derivative term, we replace QB by this commutator. And originally, so let's take a step back. Originally, we had this thing, but if you recall, in order to go from symplectic potential to symplectic form, we had to take one more exterior derivative, right? So that's the reason why it all of a sudden became this one. And as I already mentioned, because this commutator includes the notion of Cauchy slice, the integration over the space-time manifold and all of those are also included in this integral. Witten said that, okay, this is the natural thing to write down. So let me box this equation and this definition. And if this seems a bit exotic to you, no worries. We can write down the explicit correlator evaluating this thing. So for example, we can evaluate it on the upper half plane. And because this commutator is sitting at the midpoint in the upper half plane, it's z equals I. While the two other open string field insertions are given by the usual two vertex. So where this F1 and F2 are the usual conformal transformation for the two vertex. Okay. I mean, if you really want, you can also draw this upper half plane. At I, we have this bulk insertion, midpoint insertion of the commutator, and then -1 and +1, we have insertion of delta psi. And by this dotted line, all I mean is that the local chart for this left open string covers this part, while the local chart for the right open string insertion covers all this part, as usual in Witten's vertices. Okay, so this is a correlator that anyone can evaluate. But there's an issue. So let me tell you what the issue is. The issue actually was already, for example, noticed in Ted and David Gross's paper. This is the one. People in this audience knows very well that actually this point I, this midpoint, is very singular point. And what do we mean by that? It's singular as soon as you try to apply any conformal transformation which arises in Witten's star product story. Okay, so it is singular for the conformal transformations appearing in Witten's star product. So for example, say this was some star product of say 3 or 4 open string fields. Then you would like to take the conformal transformation so that you have the equally sliced pizza on the disk. But such conformal transformation has a singular Jacobian at the midpoint, as we very well know. And this arises, for example, also in the Elwood invariant story. And that's the reason why the insertion at the midpoint should always be weight 0,0 primary, if you want to be free from such singularity. Because only then, when this midpoint insertion is weight 0,0 primary, then actually it is invariant under any conformal transformation, so that you can talk about how it, in like the other things transforming in the conformal transformation without the singularity. But what turns out to be the case is that for generic choice of this Cauchy slice, okay, this midpoint insertion is not weight 0,0 primary. We are going to see that very soon. It's actually not even, it doesn't even need to carry a definite weight. Even that is not the case. So for that reason, this correlator or this definition of Witten itself is actually not well defined. And it all has to do with this midpoint insertion. And we were very confused about this, and we tried to resolve it. And the resolution is actually pretty simple. Okay, if this is not weight 0,0, let's just project it to the weight 0,0. And this is a very familiar projection operator to all of us here. This P is projection to weight 0,0 primary. And at least as written, this is a well-defined expression. I'm going to soon show you how things go in practice. But as written, we have weight 0,0 primary at the midpoint insertion, and the other things are the usual open string field insertions. We can compute this correlator or symplectic form without much difficulty. There's a cautionary remark though. So typically we say, okay, because QB is weight 0, we can always commute this against QB. Turns out that you shouldn't actually do that all the time. The subtlety is that this P, the projection, okay, first of all, it cannot always be commuted with BRST charge, since once you do that, P is now going to act on the step function, but this weight 0 projection of step function may not be well defined. So finally, let me give you some concrete expression for this. Let's consider constant time slicing. Okay, so our theta is defined using this constant time slicing. So by this thing, all I mean is that we are having a Cauchy slice, which is at constant midpoint time, and that time is with respect to this parameter b. And how do we write down an explicit expression for this type of thing? Well, we can use the Fourier transform of the step function. If you are confused about this, you can take one derivative of this. That's going to bring this down, and you will not have any factor, and you recover the usual delta function. And as you can see here, okay, first point. Back in Witten's definition, as you can see here, this is not weight 0, 0. Actually, we have infinite linear combination of this type of guy. Okay, so it's definitely not weight 0, 0 primary. So that's the reason why if you insert this in the midpoint, you're going to have a singular definition. And for our case, even if you have P, you cannot commute it against QB, because this P, acting on theta, as you can see here, weight 0 projection to this guy will basically localize this expression to P equals 0. So what this is going to do is to say P equals 0, but then you see that you get coefficient which is 1 over 0 from this guy. So that's the reason why, even though we know that P commutes with BRST charge, you shouldn't always be doing that, because P may not be well defined when acting on the theta. But as I'll show you very soon, P is well defined on this commutator. Let me actually discuss it now. So let's define. Let's give it some label. We are going to call it D. So D stands for the weight 0 projection of QB commutator with this constant time slicing. And we know how to take the BRST charge on operators of exponential type. What we obtain is the following. Okay, so here da 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 are the terms which are basically going to be projected out by P. And here you see that because we took this derivative, it brought down power of P, and that's how this singular factor got killed. And the expression we have here is completely fine expression. And once we take the projection to the weight 0 part, it's again going to localize this P to be 0, but that is fine. And that's going to give rise to the 1 over the volume vector. So here, Vx naught is volume of x naught. And we are left with this simple expression. And you don't need to worry about this 1 over volume appearing here, because in any case, when we compute this type of correlator, there is always overall factor of the volume factor, volume. And that is what's going to cancel against this 1 over volume. So everything works out. And symplectic form is independent of this volume factor. Any question up to this point? Everything good? Okay, let me proceed. By the way, I have to also mention that if you consider difference of the step function for different choices of Cauchy slice, roughly speaking, this thing, for example, if we chose, say, different constant time slicing, then this thing actually has a compact support in the time domain. And there is a theory in Fourier analysis saying that if you have a Fourier transform of function with compact support, then the Fourier coefficients are all non-singular. It's, I guess, something called Schwarz's version of Paley-Wiener theorem. For that reason, if you have this specific combination, you can actually commute P against BRC charge. Okay, so this is a well-defined thing to talk about.
Sorry, I have maybe a naive question. I'm Minjae.
Sure. Hi, Carlo.
So, is it so obvious that given any sigma, you are always going to find a 0,0 primary in the expression QB theta of sigma?
Good. So you're asking if we choose, say, some complicated Cauchy slice.
It's not obvious, right, that there is always a 0,0 strict primary inside.
I mean, that's a fair point. I mean,
so in these examples, you find it, but I was wondering, I mean, generic operator I can build that is Q of something. I'm not sure that you can always find a 0,0 primary inside.
That's a fair point. Yeah, actually, yeah, the only explicit examples that we worked out was this constant time slicing and, say, light cone slicing. In the case of light cone, it turns out that if you replace this x naught by light cone direction, then all of these are way 0,0, so they're all fine and good. So now you are saying if you generically have e to the f x naught, but then what if you have some generic function?
Maybe, yeah. Yeah,
some generic function of the spatial slices, say. I guess that's what you're asking.
Yeah.
That's a fair point. Indeed, it's actually unclear to me what we really have to do once we project this type of generic function to weight 0,0 primary sector. And yeah, I don't have a good answer for this, at least for now. Actually, for us, we were considering only the C equals 1 string theory, where we have only the single free boson, which is the time-like free boson. So for us, it suffices to make sense of data for this constant time slicing. But I think in generic space-time, whether this operation is well defined or not, indeed I agree. It's unclear to me. Yeah.
Okay. Thanks.
Yeah, thanks for the comment. Yeah, it's something that we should think about.
Some confusion of mine also. Thanks, bye.
Yeah, thanks, Carlo. Okay, let me proceed. Okay, so probably here I should say we show independence of the slicing that we are choosing for constant time or light cone, at least the cases where we understand how the projection works. So here the proof of the independence goes like the following. If we have this difference considering the time slicing, this is what we get. Okay. I already told you that you can actually move this thing inside because P is now well defined on the difference. So I didn't do much, I just moved it inside. And then, this QB, which is now acting only on this one, we can move it to the other guys at the cost of introducing a total derivative. So now, at the cost of introducing the total derivative, we moved QB to act on the open string field insertions. And because this is, theta minus theta, and solutions, we assume that they have no support at the spatial boundary. This entire thing actually does not pick up any contribution from the boundary, so we can cross it out. And this one, we know that we are talking about size all being solutions. So whenever we see expression like QB acting on psi, we can trade it with psi star psi. Okay? And then it becomes very straightforward to see that due to the usual cyclicity property of Witten's vertices, this thing actually vanishes. So you're going to land on this type of expression. And it's going to vanish by cyclicity. By the way, I forgot to mention. So delta, you can think of it as a form, but equivalently, you can also think of it as a Grassmann odd variable. And here I'm using the convention that these are carrying Grassmann oddity being odd. So what this is showing is that this symplectic form is independent of choice of this slice. And we have to actually show further properties in order to claim that this is a well-defined symplectic form on the phase space. And they have to do with gauge invariance. So we know that once we are given a solution of open string field, there exists gauge orbit of the solution. So say we have solution psi. Well, it is gauge equivalent to other solutions related in this manner, where epsilon is a gauge parameter. It's a Gauss number 0 open string field. So in order to show that the symplectic form defined in this way is independent of the choice of the representative along the gauge orbit, we basically want to consider this delta psi, how it shifts under as you go along the gauge orbit. And because this delta acts only on the phase space variables, you can forget about this part, and we are left only with these guys. And then you can actually show that using the similar cyclicity argument, the symplectic form is invariant under this shift. It's a very simple argument. And now you see why the choice of midpoint was essentially in Witten's definition. It was because we can use cyclicity argument. This is not the only gauge transformation that we have to care about. There is something called null tangent vector. Okay? So for solution psi, we can define the BRST operator expanded around the solution. And that is given by the ordinary BRST operator plus the graded commutator against the solution itself. So this is what one obtains once one expands the kinetic term around the solution. And it is well known that this new BRST operator is also nilpotent. So we have a cohomology with respect to this Q psi. and this psi exact states. What are they? From the perspective of phase space, there are no tangent vectors at the point psi in the phase space. Okay, so we have a space of solutions, and there's a point psi, and you can talk about tangent vectors, and those are basically the states that you can, describe in terms of the, say, in case you have the worldsheet CFT, you can describe in terms of the worldsheet CFT states. But then all these Q psi exact states, they correspond to the null states. So what should symplectic form do when we contract it? Against null tangent vector, it should vanish. And you can check that, okay, I'm not showing you the full detail. The full detail can be found in our paper, but actually the argument is not much different from the argument that I showed before for the case of the independence of Cauchy slice and so on. You can actually show that indeed this symplectic form contracted against null tangent vector gives you 0. Okay. So the option is that, okay, modulo the subtlety that Carlos pointed out, this omega, the symplectic form we defined, is a well-defined symplectic form on the phase space of classical solutions to open string field theory. Any questions so far?
I have one more
Sure.
question. So in the case of like a Young-Mills or gravity, when you do this procedure, you get the symplectic, pre-symplectic form, right? And these have 0 modes and you divide it out. So in this procedure, it automatically gives a symplectic form. Am I correct? Or because
so this is, precisely speaking, it's a pre-symplectic form. Yeah, I didn't divide up by the gauge. Yeah, this is actually, so to be precise, this is a pre-symplectic form, but you can always mode it out by the gauge transformation, and then you are going to obtain a symplectic form. Yeah, thanks for the, thanks for this question. Yeah, I actually had to clarify this. Yeah, this is pre-symplectic form, but later we are going to evaluate it on, specific gauge when we come to the rolling tachyon example, and then you can think of this as the symplectic form. Yeah, thanks, Atakan. I should have made it clear. So now let's discuss some physics. And because this is a story familiar to everyone, I just wrote it out in advance. So we are going to discuss energy of the rolling tachyon solution. The setup is that we always have free boson, time-like free boson CFT as part of the worldsheet CFT. And at least in bosonic open string field theory, we know that when we have a D-brane, there's a tachyon in this setup. And the question is, as I pictured before, can we consider time-dependent solution to the open string field equations of motion? And one can start by discussing the perturbative solution. So this is like, if you have a potential, what if you just slightly kick it to the left, like right? Okay. And that kicking parameter is something I'm going to call lambda. At the 0th order, we all know what the equation is. At the 0th order, there's a QB acting on psi should be 0. And we notice that there is such a candidate. It's given by this famous Cauchy deformation. And I introduced this parameter u, and this u is representing the time translation parameter. Okay. So in general, we have 2 parameters for this solution, lambda and u, and this lambda is like how you initially kicked it. So in this solution, it starts at the leading order with this Cauchy deformation. And we hope that at higher orders, we can find the solution, at least order by order. So let's write out this type of expansion for the solution. Again, first order solution is given by Cauchy. And it is very well known that there is a recursive way to write down such a solution in this manner. And I'm writing this in single gauge. One subtlety is that you might worry that because there is 1 over L naught, what if this star product includes L not equals to 0 state. Nice thing is that this cosh is basically exactly marginal deformation of X not CFT, the boundary CFT. And that actually translates to the fact that you are not going to run into such a situation. Okay? So possible obstruction doesn't happen for this specific deformation due to exact marginality. So this is the productive solution that one can write down to all orders in lambda. There is another way to write down the solution. And of course, those two ways to write down the solution related to each other by reparameterization. And that comes from the idea of background independence, which is saying that open string field solution can be equivalently thought of as a D-brane or boundary state. So this boundary state description is obtained by considering the conformal perturbation theory of X naught CFT. So basically, we imagine that, okay, we have some deformed theory where we started from undeformed X naught theory. And we are adding this cosh deformation. Okay, this is conformal perturbation theory. We have to insert infinitely many of them. Order by ordering some parameter I'm calling lambda tilde. Okay. Now this lambda tilde compared to previous parameter lambda, they are related to each other, but they are different. So lambda tilde agrees with lambda at the leading order, but it actually differs from the subleading orders. But the upshot is the following. This conformal perturbation theory actually can be performed exactly in lambda tilde. And that is how people came up with the exact boundary state description. So let me write it down. Let me write it down only for the case of u equals to 0. So this is the boundary state of the deformed theory with lambda tilde. And these are the first few boundary state coefficients. Okay. And here, this f is a function you can find in many papers, in particular Ashok's paper. And as you can see, it depends both on x naught and lambda tilde. And Ashok's observation in O2, which was brilliant, was the following. If you look at the combination of this thing, if you add the two, you get something time independent. And Ashok said, okay, it's time independent. It better be the energy of the solution. Okay? So this is the energy of this solution that Ashok wrote down. In his O2 paper. It was a conjecture in his O2 paper. Later, it was explained in the context of open-closed string field theory, as I explained before. Okay, let's look at this. So basically, we have a solution parameterized by lambda tilde and u. And the energy, as we expect, is independent of the parameter u, which is related to time translation. But it has dependence on lambda tilde, and the dependence is given by this cosine 2 pi lambda tilde. Okay. Well, another way to look at this is like the following. Okay, we have been discussing just the boundary state. How do we go back to the picture of open string field solution? So background independence tells us that for this boundary state, there exists equivalent open string field theory solution. I'm going to call it psi of lambda tilde and u. And we know how those two are related. Those two are related by the famous Elud invariant. If we compute the Elud invariant of the closed string vertex operator, which is unshelled, that is supposed to give rise to the boundary state coefficient. Well, explicit expressions are written here. I'm not going to go through the detail because this is very familiar subject that many people in this audience have worked on. Elliott made a conjecture in his paper, which is basically the statement I already made. If you compute this Elliott invariant, that is going to give rise to the difference of the boundary state coefficients. where the difference is given by when you evaluate it in the undeformed theory versus when you evaluate it in the deformed theory. And this solution is standing for the solution for this deformed theory written in terms of the degrees of freedom of the undeformed theory. Okay. There is one particular L-loop invariant which I would like to discuss here in our case, and that is something called zero momentum dilaton. Okay. This is on shell, so there is no problem discussing its L-loop invariant. And the boundary state description tells us that it is actually given by cosine 2 pi lambda tilde. And we already saw this cosine 2 pi lambda tilde here. So what this is saying is the the dependence of the energy on lambda tilde is actually contained in this L-loop invariant. And this is actually going to play an important role when we compute the energy of the rolling tachyon solution using the full boundary state description. And again, as I mentioned, I described two ways to describe this rolling tachyon solution. One is using lambda, which comes from the productive solution. The other is lambda tilde using the boundary state, and they're related, and their relation can be worked out using L-loop invariance. And this is, for example, reviewed nicely in Mate's thesis in 21. Well, okay, so far this was just a review of what people already knew. Now let's compute this energy using symplectic form. First, let's start with productive solution. So this is a productive solution that we had. And because we have expansion in lambda, we expect that we are also going to have expansion in lambda for the symplectic form itself, because symplectic form was built out of the solution. Okay, so that expansion I'm going to write like this. Okay, so recall this u was the time translation, so this psi depends on x naught in this specific combination. And the proof of the independence of the choice of the Cauchy slice tells us that if we write down the symplectic form, it will not have any explicit dependence on u, which in particular means that this energy expression can depend only on lambda, not u, as we expect. So once we write it this way, it becomes clear what the energy is. Energy is just this one. Okay, so we have a solution order by order in lambda. We have symplectic form order by order in lambda. From there, we can extract energy order by order in lambda. Good. At lambda equals 0, of course, we know that the answer should be just given by the tension of the original D-brane, which is this one. I mean, this is not derived from symplectic form, but this is what we know. And now let's consider the leading order computation. So at the leading order, the open string field solution for rolling tachyon is nothing but this Cauchy. We have just this one. And in order to evaluate the symplectic form, we have to consider how it looks like when we act by the exterior derivative. So what have I done here? So this delta, again, is the exterior derivative on the phase space variables. In our case, the parameters for the solution were lambda and u. So this delta can act only on lambda and u. This is when it acted on lambda. When it acts on u, it effectively differentiates this Cauchy, and it turns that into sinh. And if you forgot, okay, let me just bring all of these things into color. If you forgot the very definition of symplectic form, when we are using constant time slicing was this one, where this D was the commutator obtained by choosing the constant time slicing. And this is the explicit operator expression for that. And we just evaluate at this order this correlator. Okay, so all we did is to insert D into the midpoint and this delta psi into +1 and -1 in the upper half plane. This is another picture for this. And you know, this is a very simple correlator to compute. And the answer one gets is the following. What is this term? It's basically the energy contribution at this order. So let me write it down. So this one was the original tension of the D brane, but we have this correction factor. At the leading order, this can be written in terms of cosine. And because at the leading order, lambda and lambda tilde are the same, you can compare this to Ashok's conjecture or Ashok's expression, and they agree. And you can go to the subleading order. I'm not going to discuss the full detail because starting from the subleading order, one actually needs to talk about level truncation. The reason is like the following. So at the subleading order, we are evaluating still the same diagram, but the insertion of the solution now comes with higher powers of lambda and higher order solutions. And we know that this psi 2 and psi 3, they are computed by taking star products of psi 1, basically. And for that, we use level truncation. And this is the result of level truncation. So this axis is the level. And what we are plotting here is a ratio between this second order energy compared to the first order energy. And we obtain this number -1.126. And as I already told you, you can compare Ashok's expression, which is written in terms of lambda tilde, to this value, because you can obtain the relation between lambda tilde and lambda by comparing the Elud invariant against the boundary state. And that comparison actually gives rise to this ratio being -1.119. So you see that they agree with each other pretty well. So this was for the perturbative solution. I'm going to finally describe what goes on for the full solution. So full solution was written in terms of this lambda tilde variable. Okay. And the parameters for the phase space are lambda tilde and u. And as I already told you, the energy expression that Ashok wrote down was basically equivalent in terms of the lambda tilde dependence. It was equivalent to the Elud invariant of the zero momentum dilaton. So the idea is that, okay, we have symplectic form. Whatever the solution is, we can write it in this form. And we can actually try to relate this thing with this thing. One might say, okay, symplectic form, we have this type of diagram. We have two insertions of open string fields. Elud invariant, we have similar diagram. So let me draw it here. But the insertion actually is at the origin. There's a single insertion. So one may worry that, okay, how do I compare something with two insertions of open string field with one insertion of open string field? And also the midpoint insertions are different. I'm not going to give you the full detail, but I'm going to give you the ingredients that goes into the full detail. So first of all, when we evaluate symplectic form with this type of things, we also have to consider how we vary it with respect to u. But because the solution itself always comes in the form which depends only on x naught minus u combination, when we talk about how it depends on u or x naught, it can be traded with derivative in x naught. And you can transform it into the contour integral in terms of partial x. And this is how, so again, recall, this zero momentum dilaton was something like this. As you can see, this is like 2 of x, this is only 1x. You basically obtain the other x in this procedure. Another thing is that this zero momentum dilaton is actually BRST exact once you talk about the extended BRST complex. So now by moving this QB, which is in this picture, surrounding here, you can move it to this side. And we know that because psi is a solution, you can turn QB acting on psi into 2 insertions of psi. So even though originally your LOD invariant was with only 1 insertion of psi, you can actually get 2 insertions of psi, similar to the picture of the symplectic form. And using all of that, one can actually show that they exactly agree with each other. So the conclusion here is that if we compute the energy using the symplectic form, it agrees with the Ashok's expression for the energy of the Whirling tachyon solution. Any questions up to this point? Okay, so to summarize, what I did today is that, okay, we have space of solutions in open string field theory, and one can define the phase space, which is basically space of solutions, and then one can equip the phase space with the symplectic form defined in this way, which was originally motivated by Witten's prescription. And you can use the symplectic form to compute physical quantities. And in this example, we computed the energy of the rolling tachyon solution. It will be interesting to consider similar situation for other types of interesting solutions. What happens if you have multiple libraries and so on? I mean, again, our original motivation was to consider quantizing such a classical phase space and get the quantum open string field theory. We are not there yet at all, but I think it's a very important direction to pursue. And finally, I wonder, this is more mysterious to me, but I wonder if one can define similar notion of phase space and symplectic form on the space of closed string field solutions. I mean, one of the reasons why, the nice picture we have here really, made all this cool story was because we already have many solutions. And in open string field theory, that is due to the special form of Witten's cubic string field theory. But we don't have such a form for closed string field theory. So yeah, probably that's the reason why our insights are quite limited when it comes to the space of solutions for closed strings. But it will be nonetheless interesting to really ask the question whether we can define this, notion. Because in the theory of gravity, people do this all the time. So we expect that we should be able to do something similar for closed string field theories also. With that, let me end here and thank you for your attention.
Thanks a lot for the very interesting talks. So is there any question for Minjae?
Yeah, I actually have a question, but if anybody else have questions, they can go ahead.
Okay, I would have a question as well.
Sure.
Can you hear me?
Yes, I can hear you.
Okay, so in the very beginning, also in Witten's answers that you discussed, you introduced like the boundary contribution coming from the kinetic part of the action. So
yes.
Is it so obvious that there is no contribution from the cubic term as well?
So for a cubic term, we actually use the cyclicity of the vertex to move the variation around.
Yes, I know, but wouldn't that be also violated in presence of a boundary? because the cyclicity basically follows from conformal invariance, right? That you have a dual conformal transformation, but in some papers it's argued that conformal invariance is broken if there is a boundary in target space present.
Sorry, so here I'm not talking about target space in the presence of boundary.
Okay.
Yeah, that was my entire context. So I'm not, so okay, even, yeah, for example, yeah, that's actually the question I guess Atakan also addressed in the middle of the talk. So indeed, one can do the covariant phase space formalism in the presence of the boundary, and such a thing is explained here. But for today's talk, I was actually restricting myself to the case where we don't have the boundary in the space-time. And I think, yeah, I don't have much to say when we describe string theory in the presence of boundaries. Yeah, for me, the cleanest example for this really was C equals 1 string theory, where we have just time-like free boson and the Liouville, C equals 25 Liouville. In the presence of boundary, of course, all this story will get modified. And yeah, if you want to study this case for the case of, say, GR or Lagrangian field theory, then Harlow and Wu's paper has a beautiful description of it. Yeah. Yeah, sorry if it was not.
So let's say the initial time or final time, or what, this would not count as a boundary in target space time, or?
Good. So I mean, typically when we describe the boundary condition, for example, of the solution, we are, so at least in this context, we are assuming that they decay at space-like boundaries. In time-like boundaries, we are not necessarily assuming that. But here, basically, yeah, how should I put this? Yeah, I mean, again, this time-like free boson does not have the boundary, right? It's just a usual real line. Yeah, it's just given by the usual X naught CFT. So there is no boundary term coming from such time-like free boson. And when I say this total derivative term, so it's a total derivative term due to this thing being BRST charge and this integral being the Witten's convolution. Yeah, I think, yeah, that's the best I can say.
Okay.
Yeah, does this address your question?
Yeah, more or less, yeah, okay, thanks.
Yeah, thank you.
Hey, so I have a question about this projection thing that you put P. So, I mean, in principle, can I justify that prescription by, say, like working with adding some stops or something? Then the midpoint won't be, well, maybe not stops, but like the hyperbolic ones, say, and that's perfectly regular point. Then try to write, deal with that polynomial theory and take the limits. Do you think that is it possible to recover that the projection operator?
Oh, great. May or may not be. So first of all, I don't think that there will be any obstacle in trying to define the symplectic form in the more general choice of string vertices. Of course, you'll have some non-polynomial vertices, but it's fine. I guess there should be no problem defining it. Whether in the limit where you actually take them to the Witten's limit, you recover this expression or not, it's something that I expect, but it's something that's also hard to say because it's very singular limit. Yeah. So I don't have a good intuition behind this. Yeah. I
somehow
don't have
like it should this. Yeah, fair enough. Like, because what is going to happen is that there will be more correction to the symplectic potential. And somehow, like when you take the limit, that will result in this like projection operator, which will be very like singular in certain sense. Like I cannot see how it will come from, but yeah, I was just curious.
Yeah, I agree. Yeah, I mean, typically from the geometric perspective of string vertices, one can describe this limit, quite freely.
Yeah.
But whenever it comes to explicit, correlators and so on, there are so many singular things happening. And
because in principle, like this is something like we want in this Gauss-Dilaton story with Witten plus Elwood coupling, right? Like in a sense that that's the same problem. Somehow we want to place this ghost dilaton to the singular point in the Elwood invariant.
Right.
But like putting like this primary P, might not, it won't solve that problem because, that kills this ghost dilaton term.
Right.
So I was wondering like if somehow like you can get some insight how this like a right way to do it will come from this prescription, but
yeah, it's unclear to me. And, by the way, I forgot to mention, in this computation, ghost dilaton at the midpoint insertion also arises. But the reason why
I've seen it's like there's
the reason why we actually do not quite need to worry about it is because symplectic form is sensitive only to the exterior derivative of the solution.
Yeah.
And we know that pure ghost insertions are going to have no effect on the parameters of the string field solution.
Yes.
So that's the reason why it naturally dropped out
like,
in the discussion. Yeah. But indeed,
so somehow this rolling solution doesn't affect the like a string coupling. It shouldn't change, right? Like
right. It is a classical solution.
So that's a physical.
Yeah.
Exactly.
Yeah.
Good. Yeah. Okay. Anyway, thank you.
Yeah.
Great.
Thank you, Atakan. Yeah.
So do we have more questions for Minjae?
Thank you.
Okay, so if we don't have, so I will stop the recording, and if someone is shy and want to ask off recording, I will, we can.